We can start. Okay, so we're very happy to have Maria here, professor at Princeton, graph theorist, very famous, and she will tell us about some graph theory, I guess.
That's good. All right, well, thank you for inviting me and thank you for coming. Please ask questions. Jeff Kahn likes to say, I'd rather you understand part of something than nothing of everything. So there's no kind of, I'd like to get to the main theorem, but it's somewhere in the middle of the lecture and everything after that is optional. So do ask, please start. So this is joint work with Sophie Sprockel and her student Sepper Hajbi, but this is also based on a series of 18 papers. So and there are other authors to some of the papers, so a lot of people contributed to this work. All right, so so for the last 5 years, I've been thinking about the concept of treewidth. And let me tell you what tree decomposition is, let me tell you what treewidth is, I'll do some examples, then I'll start, and I'll actually tell you some theorems. So tree decomposition, so you have a graph G, and you want to represent G by a tree, right? To us, all trees are simple, and graphs that are not trees are getting more and more complicated. The further you are from being a tree, the more complicated I think you are. So I'm going to take a general graph G, and I'm going to try and represent it by a tree T, and there'll be some function pi, and I'll write the rules and I'll do some examples. So the rules are pi is a function from the vertex set of T to the set of subsets of G. Right? So you think of a tree, and to every vertex of the tree, you assign a subset of vertices of G. And I want it to be a representation, so there need to be some rules, and there are 3 rules. The first rule is for every V in G, there exists T and T, so that V is in pi of T, so every vertex is captured in some bag. The second rule is every edge is captured in some bag. Right, so far, I just tell you what needs to be present. And now the last rule says you can just throw things in however you like. There needs to be some order. And the order is if I put a vertex of G in this vertex of T and in this vertex of T, then I have to put this vertex in every bag on the path from here to there. Right? It's a tree, so it's a unique path. So it means something to be on the path from here to there. And every vertex if V is in this bag and V is in that bag, then V has to be in every bag on the path between. So I'll write it differently, but I say it like this. So for every V in G, if I look at the subgraph of T induced by vertices in whose bag V lives, this subgraph has to be in G. All right, so
The subgraph has to
Three.
a tree. So let me do a couple of examples. So here's example number 1. This is G, and this is an extra easy example because G is a tree already. So this whole game is a little bit of a waste. I'm going to do it anyway. So this is G. Vertices of G have names. And then this is T. And I'm going to use the same T. So now all I need to tell you is which vertices of G need to be in each of the bags. Right? So here's an algorithm how you would do it. You pick a root for this tree, and you say, and then for every vertex of G, there's a unique path to this root. And so it has a unique neighbor in the unique path to the root. And that's what I'm going to put in that bag. So for every vertex in the corresponding bag, I'll put it and its unique neighbor in its unique path to the root. So here the root is 3. For example, for 1, its unique path to the root is 1, 2, 3. Its unique neighbor and its unique path to the root is 2. So in the bag for 1, I'm going to put 1 and 2. And here it's going to be 2 and 3. 3 is already there, so it's just 3. 4 and 2. 6 and 5, 7 and 5, 5 and 7. Right? So that's a tree decomposition. You can check the rules for this. So now, so far, this is not a great gain. I started with a tree with 1 number in every vertex and ended up with a tree with 2 numbers in every vertex. But we'll see why it's a gain in a little while. Yes.
So you can, I guess, if I'm understanding the definition correctly, you can just put every vertex in as like the set for VT could be like all vertices.
That's it. You can take a 1 vertex tree and 1 bag and then.
But you're trying to like minimize the
Right,
size.
so
of the
I'll get to what I'm trying to minimize in it, but exactly. Simplest thing is just take a 1 vertex tree and.
Or take a spanning tree, right?
Again?
Or take a spanning tree and just take 1 in every.
No, because you need to capture every edge.
Oh,
Yeah, putting a lot of stuff in 1 vertex is a good idea, but putting a little stuff in 1 vertex is hard.
You need to have an edge inside a bag, so you had to have 2 vertices per bag?
No, here, this bag only has 1 vertex. It's the other way, every edge needs to live in some bag,
In some bags, so like
but the other way,
the tree on the left is not a good tree decomposition, only the tree on the right.
yeah, right. Right? Okay, so let's do a slightly more interesting question and a slightly more interesting example. Let's do something that's not a tree. And the tree I'll use is this. Oh, and the way I think about it, let's forget 1. So now what's left is a tree. Let me use the algorithm I described before. So I'll call 4 the root. So the past 2 4 are 2 3 4 and 6 5 4. So remembering that, it's going to be 2 3 3 4 4 5 4 6 4 6 5 6 here maybe. And now I need to put 1 somewhere. And there's some rules. So 1 needs to go, the edge 1 2 needs to be somewhere. So let me add 1 to here. The edge 1 6 needs to be somewhere. So let me put 1 here. And now I remember the last rule that if 1 is here and 1 is there, then 1 has to be everywhere in the middle. So I'm going to put 1. And that's tree decomposition. So here I do consider it a gain because the graph got simpler, right? This graph had a cycle, this graph has a tree. To me, that's all. All right, so that's a tree decomposition. So now what's the difference between, oh, let me just say 1 more thing. So if the tree is a path, right? If T is a path, that's called a path decomposition. The path. This is path. So for example, this thing, it's tree decomposition, but it's actually also a path decomposition. Okay, so now let's formalize what the difference is between using a tree decomposition that you suggested, where I just put all the vertices in 1 bag, versus this somewhat clever things I was trying to do. So I want to measure how simple my tree decomposition is. And by simple, I mean, my goal is to take a complicated graph and then represent it by an easy graph, which is a tree, in such a way that in every bag, there's not too much complexity. So what I want to measure is how complex the bags are. And the simplest way, right? So in that sense, putting all the vertices in 1 bag is a really bad idea because the bag is as complex as the graph you start with. So let's, it is now fashionable to define many different ways to measure complexity of bags. But in today's lecture, I'm only going to talk about the classical one, which is just the size. So given a tree decomposition, its width is the maximum size of a bag. And now, given a graph, I want to know how, I guess, narrow a tree decomposition I can find, how small I can make the width. So the treewidth of a graph is the minimum overall tree decompositions of the width of the decomposition. Okay. So it's kind of what you expect.
It says that every cycle has width.
That's right.
What cycle?
Oh yeah, let me put in -1 here because people.
So is there a way to read back the graph from the decomposition? Like what,
So you'll read a supergraph, right?
Yeah, I mean, you can always take everything in the bag and just.
That's right, but that's all you know. It's not one-to-one.
So it doesn't make sense to measure the difference between the supergraph and the original graph as the complexity. Or as the not complexity, as the.
That will give you something else. That will kind of, that measures how close your graph is to be chordal, but that doesn't measure how complex the tree decomposition is.
But I mean, I guess my question is, so you are forgetting something when you're doing.
Absolutely, it's a representation. It's not a tasteful representation.
Kind of what, intuitively, what does it mean?
Right, so let me talk about this next. Let me just give you one more definition and then I'll try to give some more intuition. So we have treewidths and then there's also pathwidths. And what pathwidths is, you probably guessed, it's when you're not allowed all trees, but you're only allowed the minimum of all of the p type. Path calculation. Oh, so now we have all the definitions. Now I can chat a little. Split. So we would like to say that what Treewidth measures is how close your graph is to being a tree. Now, what does that mean? So the kind of first thing that comes to mind, trees are very sparse. So, and on the other hand, graphs that are very dense, they have big treewidths, like for example, the treewidth of the complete graph. It's T-1, the treewidth of the complete vector graph, ETT is T. So big dense certainly does not help you being close to a tree. To be close to a tree, dense graphs have large treewidths. But there's another kind of graphs which are very, very sparse and they still have large treewidths. And that's if you take the green. You take a graph like this, it's a planar graph, so it's already pretty sparse. And then subdivide edges as much as you like. So now it's really as sparse as you want. And yet this has huge treewidths. The treewidth of this graph is I think at the minimum or maximum, but something between the rows and the columns, probably the minimum between the number of rows and the number of columns. So let's say, so I don't embarrass myself, let's say this is k by k. So the treewidth of the k by k grid is k. So being sparse or dense is not what we're measuring when we think about treewidth. And it turns out what you really measure is, so here's another property of a tree. You can delete, if I give you a tree, you can delete a vertex and break the tree into roughly equal parts. That's the property Treewidth is trying to mimic. So you want to say, I can delete a small set of vertices, in this case, bounded size set of vertices, and break the graph into roughly equal parts. Roughly equal means both sides are at least 1%. And that turns out that's very good for algorithms. It's nice for describing the structure of a graph. So, but that's the measure we're after. So small treewidths. It can only exist a small, balanced separate.
Recursively.
Second?
Recursively.
Recursively, that's right. That's right. Oh, yeah. All. Right. Okay, so I was in the middle of us answering a question, but I forgot the question. Is this related to the question? Okay. Okay, so now let me just say another way to think about small treewidths or small pathwidths. So let's do small pathwidths first. Small treewidths, the same except you're saying a tree instead of path. So you take a bunch of small graphs. And they're all tiny. And now what I'm allowed to do is overlap consecutive ones. And if I can describe my graph like that, start with a bunch of small graphs, you may overlap consecutive ones however you like, but not far apart ones. Not independently far apart ones, then your graph has small treewidths and small pathwidths, pardon me. So G exchange. Overlaps. Treewidths. And now, what about treewidth? Well, it's the same, except you're not just allowed to overlap consecutive ones. You think of them as being in a tree pattern, and you're allowed to overlap ones that are adjacent in the tree. All right. So that's the kind of introduction to treewidth and pathwidth. Let me say what's good for this. Oh, treewidth is good. Recursive. You take the balance separator, guess the solution of whatever problem you're solving on the separator, see if, look at extensions to the left, extensions to the right, and see if you can put them together. And because the left and the right are both linear inside of the graph, complexity works out to be polynomial.
There's, I guess, many incomplete problems for which you can do it polynomial.
Exactly.
If the treewidth is one.
Exactly. Coloring maximum independence set. Also not.
If something like this exists, it's easy to find.
It is. So that's I always forget to say that. Somebody always asks it actually. So if I give you a graph and I promise you it has treewidth 1,000, you can find in linear time a 3 decomposition with width 1,000.
But maybe it's exponential in the parameter thousands. No?
That's
Yeah, 1,000 is the next.
1,000 is the next one.
Yeah.
But
Don't try it at home.
all right. Okay.
Sorry, you said linear time, so 1,000 is not in the.
The exponent.
Maybe the
constant.
constant.
Leading constant. Yeah.
1,000 times.
Yeah.
It's like one of these fixed parameter properties.
This was an example of a graph that has small treewidth, or this is
It's pathwidth. That's if and only.
never mind. Or
If and only.
this is also like how you described it.
Yes.
Okay.
Okay. Anything else? Okay. So now I've advertised treewidth and pathwidth. No question. You look at our classes. No? Okay. So now the question that I really want to think about is when is treewidth bounded or when is pathwidth bounded? Now, of course, you need to ask this question a little bit intelligently, because for one graph it doesn't make any sense. You need to ask it for an infinite class of graphs, and then how do you present your infinite classes of graphs? So I'm going to ask, what do I need to exclude so that the class with these things excluded has bounded pathwidth of treewidth? Question for which H or H in family of graphs. You H3 graphs have bounded.
Minor clause, the family.
Well, minor clause is the same as for which H3 or free is as minor.
Yeah. So looking for it, that's but
So I'm gonna vary this freeness in the moment. It's gonna be different kinds of things.
sorry.
I'm gonna talk about different versions of
Okay,
freeness.
okay, good.
Okay, so so the 3 kinds of freeness I want to think about is minor subgraphs, actually 4 minor subgraphs, induced minors, and induced subgraphs. And maybe you don't know what an induced minor is because it's a new thing, so I'm going to tell you what that is. But first, let's do the ones that have been known for a while. So it's a theorem of problems with zero. Oh, 1990 roughly. For every T, there exists C, so that the G is B by T grade free. minor tree, then treewidth of tree is at most, right? So if you forbid a big one of those, get the subdivisions. If you forbid a big one of those as a minor, then the treewidth is bound.
Maria, define a minor.
Should I define a minor?
Oh, maybe remind us.
Sure. Okay, so if you have graph H, maybe I'll define an induced minor while I'm at it. So if you have a graph H, you say H is a minor of G. So let's say the vertices of H are H1 through HK. So now then in G, I want connected subgraphs X1 through SK. So that if two vertices here are adjacent, there is an edge between two guys. If HI, HJ is an edge of H, then some of G is one end in Xi and one end in X. Right, so for example, this graph contains this is a minor. This
It's not if and only if, so if they're disconnected, it's still okay to have an edge.
that's right.
Yeah.
That's right. So this is a minor of that because, for example, I can say this is X1, this is X2, and this is X2. And I can say all kinds of things.
So another way of saying it is that you can obtain H from T by removing edges and subtracting it.
That's right. That's right. But this is a kind of nicer way to, easier way to think about it for me. Okay, so that's a minor. So now induced minor. So you know about induced subgraphs. Right? A subgraph means you're allowed to delete vertices and edges. Induced subgraph means you're only allowed to delete vertices. So same deal with minors. For minors, you're allowed to delete vertices, delete edges, and contract edges. For induced minors, you can't delete edges. And in this definition, or in this way of saying it, what you get is H is induced minor of G if you can find this connected subsets Xi, and this is if not. Two things that should be adjacent have an edge between them, two things that shouldn't be adjacent don't have it. That's the difference. And somehow I've come to believe that induced minors to induced subgraphs are what minors are to subgraphs in some sense. Okay. So the Robertson and Simonyi theorem tells you what you need to exclude as a minor. Now, it would be nice to make it a theorem about subgraphs because subgraphs are much more basic than minors. And you can. So let's first tweak the theorem for minors. So this is a grid. Let me tell you what a wall is. So what you do is you remove every second vertical edge. Like this. That. This. And like that. Another one just so it looks better. What did I do?
You skipped one.
Skipped one. So you can see why it's called a wall, but it's good to know that it's closely connected to the grid because with a wall, it's hard to tell. Like I'm going to call this something by something wall, and it's hard to tell what by what a wall it is. But if you think of it as coming from the grid, then it's clear. So like this.
It's different than a grid.
It's different than a grid because this is cubic and the grid has degree 4. So it's definitely a different graph.
Okay, yeah, but.
For minors, it's the same. One is a
It's the
minor.
same. Okay.
This is a minor of that, and that is a minor of this. But for there's a graph, it's different.
Yeah.
So let me restate this theorem, which everybody points out that this is just free. Wall here, but now I can say the same thing for graphs. For every T that exists C, so that if G does not contain a subgraph isomorphic to a subdivision of the whole, I'll say W can see say, then the Treewidth of G is lost. Right, so now the same thing for you can say it for minor, you can say it subgraphs, but then you need to include all, you need to forbid all subdivisions. You need to include all subdivisions in the thing that is forbidden. Okay, so that's for subgraphs, and that's been.
Oh, yeah, it's a generalization of the general Robertson-Seymour theorem for induced minor.
No, not yet.
No. Not known, or it's known not to be true, or
Well, it's not known what. I mean, are you asking if this theorem is true for induced?
no, I'm
minors?
asking, the general Robertson-Seymour says that if
What happens if you exclude a minor?
minor clause, then it has a finite list of obstructions.
Mhm.
These are an analogous thing for induced minor.
Oh, you mean the well quasi-ordering?
Yeah,
I think it's I think it's not well quasi-ordering, but I may be. Jordan, do you remember? I'm pretty sure it's not well quasi-ordering. It's I don't want to swear with my life. Okay.
So just, I'm kind of confused by these two terms.
Okay.
Is one like clearly implying the other, or?
Yes, it's so in fact they're equivalent, but this immediately implies that one of them. So let's see, if you don't have, if you have a graph and you don't contain minors of this type, then you definitely don't contain subgraphs which are subdivisions, and so the Treewidth is bounded, like whichever one you believe.
Because wait, you changed, there was a grid before, now both of them.
Now both of them are walls, but for minors, wall and grid is the same.
Okay, I see.
And it's also true that if for a cubic graph, you contain it as a minor, if and only if you contain its subdivision as a subgraph. So it's really kind of, everything is, it's hard because if and only if theorems, it's always hard to formally say what applies what, but between friends, everything is the same. Anything else?
yeah, why do you prefer one to another?
I don't know, I think minors, I think subgraphs.
Subgraphs are more with, yeah.
I mean, the reality is it's better to work with minors than in the end specialize it to subgraphs, but I think good. Think about the final product. Subgraphs. Anything else? All right. So the question I want to ask is, what if I want to think about induced subgraphs and maybe induced minors? And somehow the question that was originally asked was about induced subgraphs, and then people realized that induced minors is a good intermediate status. Okay, so it is this. Question which H, the class is C of H, so that the class, every G with no induced subgraph isomorphic to a member of H. The Treewidth of G is at most. Right, so now, from now on, I shouldn't say now, but now I want to think about the induced subgraph. Okay, so that's, so you have to, we learned some lessons from minors. So we need to exclude the complete vector graph, must exclude, which must contain big complete graph, big vector graph, and subdivided wall. Right? Because if you don't exclude those, they're gonna be in your class. And here's something you can do. You can, if you're used to thinking about induced subgraph, here's something else you can do to a wall, which is not does not affect anything if you're thinking about subgraphs or minors, but it is important for induced subgraphs. Take the line graph. So what does it mean? If you don't know what line graphs are, change every claw junction to a tractable junction. I'm not going to draw them all, but that's what I did. I changed every claw to a triangle. And that's another graph. It has the same tree width as the one with the claws, but in the containment of induced subgraphs, it's two incomparable things. No wall is a subgraph is an induced subgraph of this, and none of this is an induced subgraph of wall, right? Because it's claws and triangles. So another thing that you have to exclude is that's the line graph.
Is it clear why like the treewidth is maintained in this kind of transformation?
So it is just the simplest thing you can do every time you had this vertex, put this whole triangle. Something like that. Maybe every time you had one of those three vertices, put this whole triangle. And like maybe it got a little bit bigger, but
Not so much.
the other way it's really the same because 3D composition of this is also 3D composition of the one where the edges are missing. This way you need.
And it doesn't work with the from previous ones with the like the line graph. I mean,
so the line graph of this contains a big one of those.
okay.
The line graph of this contains a big one of this. Somehow, in principle, you should, but in practice, you don't need to. You can just tweak the parameters. But with those, it's really you will. So let me call those T basic obstructions. Okay, so now one might optimistically hope that this is it. We got them all. If you exclude a T basic obstruction as an induced subgraph, then you get a class of bounded Treewidths. But unfortunately, that's not true. In 2019, Sintiani and Trotnion contracted a class of graphs. So it's a class of graphs that don't have K4 and don't have subdivisions of, sorry, not K4, K3, and simple words. And don't have subdivision of K to 3. Don't have subdivision of this. And every K C, it's a subclass of that, and for every K, there exists G, there is a G. So it's really no hope, right? These have K to 3s, these have subdivisions of K to 3s, and these and those have triangles. And this is a very nasty counterexample. Basically, at the moment, what separates us from proving an analog of this theorem for induced subgraphs is understanding this construction. This construction seems to be just because you 100 left, so you get it from here and then you can generalize that way. From there, you can generalize it this way. So, anyway, but they constructed this example, and so it became clear that we need to exclude more things. But there are two kind of neat things about this example, this family that they were thinking about. Let me just tell them to you. So fact one is, and that's a theorem of components. If your ambient graph has bounded degree, then these basic abstractions are enough. For every C and delta, that exists C, so that exists C, so that if G contains no C basic abstraction and the maximum degree equals delta, then the treewidth of G is at most. So if I tell you that the ambient graph has bounded degree, then this trick doesn't work. It's really just basically the same as that theory for induced subgraphs. Contains as induced subgraph. Yeah. So, and then the second theorem is that even if you don't say bounded, but you're just a little bit less greedy, instead of asking for bounded treewidths, you ask for logarithmic treewidths. So the beds will not be size 100, but they'll be much, much smaller than the graph you started with. Then it's true. That's and that's the entire Charlie, it's Nili and Sepper and Sophie. So plus this C, so that for every 3 sub K to 3 and 3 again is an induced subgraph. G, the treewidth of G is mod 3 times log the number of bits. And so this is I like graphs of logarithmic. You know, for algorithms they do the same thing. You can still test all test all solutions on the middle. But seems to be a lot worse. We cannot prove that all graphs with no T-basic abstraction have logarithmic treewidths, but I suspect it's probably true. Just we have it.
But if you're true, you don't need this, you only need that they don't have triangles. So
Well, this is a weaker theorem, right? This when I'm,
the conclusion is weak, but
the assumption is stronger. When I exclude those,
yeah, very good.
okay.
So really, you think you don't need the weaker or the stronger assumption?
Yeah, I mean, maybe I would have to say log to some power. But I suspect.
Is any polylog okay for algorithms, or because you're running some exponential?
No, yeah,
log is really-
you get quasi-polynomial. Unfortunately.
I guess in this construction, the treewidth is bounded by is logarithmic.
That's right. Actually, the pathwidth is logarithmic.
Okay.
Generally, the algorithms are n to the treewidth power over to some.
Say again?
The algorithms will run in time n to the power, which is only the treewidth.
So it's a little bit better because when the treewidth is logarithmic, they're actually polynomial.
You just need to enumerate.
Yeah, you need to
But
enumerate.
if it's polynomial,
Right, it's polynomial. Okay, and let me tell you one last theorem. All the curiosity, that's something I need for the rest of my talk. At least we're just information. The next theorem actually might choose if I ever get to the proof. Yeah. If P contains, so for every TR there exists C, so that if P contains no T basic abstraction used and no subdivision of I'll call it an R brick, and that's going to make what an R brick is. R brick as a subgraph. Then the treewidth of G now I'm done what an R brick is. So you start with KR, right? You take graph on R vertices, right? And now you replace every edge by R edges. So if I did all of them, this would be 4. So if you don't contain the basic abstractions and induced subgraphs, and you don't contain this, a subdivision of this, as a subgraph, unfortunately, then the Treewidth is bounded. Now, of course, my trouble is that this is a subgraph and not an induced subgraph. If it were an induced subgraph, I would contain anything I want. But somehow now the question becomes, how can I exclude these subgraphs by forbidding induced subgraphs? What induced subgraphs are unavoidable in graphs like that? Okay, so that's a theorem. That's a theorem I'll use, and what you can do using this theorem. So, like for example, what if I say I exclude T basic abstractions plus one more graph? Well, you can use this theorem to characterize this one more graph. What if I exclude all T basic abstractions plus a finite family of graphs? You can use this theorem to characterize a finite family of graphs. These are sort of hard work, but you can do it.
What do you mean by that? Use this theorem to.
So you can assume you contain this, and now you start analyzing what kind of things, what kind of induced subgraphs are unavoidable in this, and you can get a rich enough family so that you can then prove it's necessary to exclude them in order to bound to it.
Okay.
And so maybe let me tell you one more thing in this direction. Right. So what does it mean? It's necessary to exclude and to bound to it. Well, I need more graphs of large treewidth, right, in order to say it's necessary to exclude them. I'm not going to get any new necessary abstractions from this. This is already optimized. So let me tell you 2 more important families of large treewidths. Large treewidths. So one is take many paths, generalize no edges between them, and take many vertices, and give every vertex a neighbor in every. So this contains KTT as an induced minor. Half of your sets are this vertex, half of your sets are this path. It has large treewidths, and it doesn't contain any of those guys. So it's really new. And you can generalize it a bit. So here I said everybody has one neighbor on every path. You can give it a bunch of neighbors, but what you should not do, the neighbors should be kind of aligned. Like first, he should finish having neighbors, and then he may start having neighbors. And then after he finishes having neighbors, he may start having neighbors. And the reason to do that is because I want to keep it independent from that. If I'm allowing them to go crazy, then, for example, you can get complete back diagrams, or you can even get walls.
This will be planar.
This is what?
Will be planar.
This will not be planar because it has a big KTT minor.
I know.
But something like that. If I look at one path, it's planar. Okay, so that's one. And the other one is called, and this was constructed by Holt and Davis. Davis. And I would say it in this order because he did it 10 years before he did it, but everybody forgot. So it's actually independent. And then the second example is called the Death Star. It's constructed by very many people, so I'm not going to tell you all the names, but very many people together. And what the Death Star is, you start with a path, and you take a vertex and you give it a neighbor in the middle of this path. And now you take another, so that this created 2 subpaths. Now you take another vertex and give it a neighbor in each of these subpaths. And this created 4 subpaths. Now you take a vertex and give it a neighbor in each of these 4. And you keep going like that, and it's a Death Star if you're familiar with the source. And the Treewidth of this thing is how many vertices you added. And so you can generalize most of them a little bit, but maybe not tell exactly how you generalize them. Okay, so now we have the basic abstractions, and we have those abstractions. And my notes, this is X abstractions, this is called Y abstractions. So I like to reserve the right to refer to them that way if I need to. So let me keep this board because this is board later. And now let me finally get to Pathwidth. Right, so now I told you more or less everything communicable like I can explain about Treewidth. But now let me get back to Pathwidth. Or let me get to Pathwidth. So for minors and for subgraphs, we're in exactly the same situation as with Treewidth, except less complicated graphs have large pathwidths. You don't need to exclude a whole wall to get big pathwidths. It's enough to exclude a binary tree. So these terms become for every t that exists C, size of G is T minor free for every it's 3T. Then the pathwidth is bounded. And you can say it for subgraphs, so you need to be little careful here, isomorphic to subdivided binary tree. Big T is a binary tree, let's say of high T or something like that. Then the Treewidth is bounded.
But
Yes. So somehow you're more or less in the same. And then if you want to think about induced subgraphs, so you go here, and instead of excluding all, you say tree, and instead of excluding line graph subdivision of wall, you say line graph subdivision of binary tree. And you've kind of come to the same place. And then there's a nice theorem of bottom. Oh, and maybe I should say that these are also theorems from the, this is actually a theorem from 1983 of Robertson and Seymour, and then Distel had a simpler proof in 1990, and then Seymour had a really easy proof in 2023. I'm going to teach the simple proof in my class next week. But to our business, it's important that Higginbotham proved that if I want to understand what induced subgraphs I need to exclude to get bounded pathwidths, it's enough to think about Treewidth. So somehow kind of he closed this gap. I can think about a graph of large Treewidths, which gives him more information than large pathwidths, and maybe not more, but at least we know. It so happens that we know more about them than large pathwidths, and I only need to look for those things. Let me write down the theorem of Higginbotham. Understand what I mean? I write the theorem myself, but I can't spell his name without feelings. So. Perfect. There exists C, so that if G, so let me get my notation. So these are going to be XT abstractions. I don't want to call them T basic because T basic was something else. So that if G is XT3 as an induced subgraph, and the Treewidth of G is a small star, then the path resolution. So it's enough to understand graphs of big treewidths that don't contain those. It's kind of close this gap, even though those are necessary to exclude for pathwidths. By this theorem, it's enough to understand graphs that don't contain those and have large treewidths. And what he really does, he finds a big complete minor. The way the proof goes, if you don't have a big complete minor, you can get small pathwidths by just excluding those things. And if you do have a big complete minor, then the treewidth is big.
What is the relationship between C and R?
I don't know, multi-exponential. So big that it doesn't seem worth remembering. Okay, so now let me tell you the main theorem that I wanted to get to. For every t exists C such that if G is xt3 and yt3, maybe generalize what the thing now, reveal yt in a second. As an induced subgraph, then that's what so we have a complete induced subgraph characterization of graphs with large pathwidths. So again, xt means no big complete byte graph, no big clique, subdivision of a binary tree, line from a subdivision of a binary tree, and you have to exclude them because they have big pathwidths. And then yt are those guys. So what did you say? Something about what I really mean when I say generalized. So you start thinking about this. You take many paths. And now what happens in this graph is that as I walk along a path, if I walked from neighbors of 1 to neighbors of 5, on the way I saw neighbors of 2 and neighbors of 3 and neighbors of 4. So now the rule is if I walk from neighbors of I to neighbors of J, I'm allowed to miss neighbors with most C people between I and J, or most T people between I and J. So it's kind of, it's almost orderly like that, except there's a little tweak. And then, so that's not right, but, and then the second one is, you take a bunch of paths, and now in every path, you want to see that. And for this one, you don't even have to have a bunch of paths. One path is enough as an obstruction, like it only has large paths with. And so in every path, you see one of those. And that's it. So, okay. So that's what's generalized to YT means. But it's some 2 infinite families of graphs you can construct. All right, I don't know, should I say something about the proof or should we declare success? Okay.
Use the bigger yours.
Oh, yeah, that's true. Now I just cancel the background. So a key trick in the proof is to think about induced minors. We kind of got there slowly, so let me first think. So step 1, think about induced KT minors. There's an induced KT minor in your graph, so what does it mean? And then like this is then, so it's R connected graphs here and R connected graphs there, and edges like this are present, horizontal edges are not present, that's what the KR induced minor is, and you analyze what they look. And you can really describe their structure very clearly, because what you say is, what is this connected graph? I mean, maybe there was a lot of stuff there to begin with, but really all I need is somebody with a neighbor here, and somebody with a neighbor here, and somebody with a neighbor here, and somebody with a neighbor there, and some way to connect. And there's a theorem that tells you exactly what they look like. If I have, so the theorem is, if I have a connected set, and a big subset of vertices, all with neighbors here, and I want to extract a minimal subset of this that contains neighbors of all of those, there are 4 things that can happen, maybe 5. So maybe it's a subdivided star like that. Maybe it's a liner from a subdivided star. That's a big click and some paths leading you to where you want to go. Maybe it's trying to be a star, but this vertex became a path. So it's a caterpillar. Subdivided caterpillar. And again, these are the vertices that you were trying to reach. Maybe it's a liner of a caterpillar. These are the vertices you were trying to reach. And then there's one more, the nasty one, because of which nothing works. Maybe it's a path, and your interesting vertices just hit it. And that's a bit. But these tend to give you, well, actually, that's just a big bit.
One of this is from a stable set.
So this is just a lemma. I have some connected graph, and I have a bunch of vertices. They're called S. It's called H, and I want to know what's the minimum subgraph of H, what's the minimal subgraph of H that catches a lot of S. I don't promise to catch all of S, but I promise to catch a lot of S. And I can find something orderly like this in H.
You know, the bottom vertices, on the right hand side, they form a stable set. Are they?
It doesn't matter, because the theorem is about subgraphs of H catching them all.
Or subgraph?
Induced subgraph of H catching them all. Oh, you're asking me why there are no edges between those?
Yeah.
You can make them a stable set, right? Because again, the theorem is about this and the cross edges. So you can assume this. So then what you do is you say, well, what's a minimal bit of this that catches maybe not all of these, but many? And it's one of those. And now just take this many of this and now work on him. And you do it many, many times, and there are finitely many combinations, and most of them give you something, and all of them give you something. And I don't want to say any more about that. Because from now on, it's not illuminating anymore. And by the way, that's not how the proof is written. That's how I like to do this proof, but the person who wrote the paper likes a different version of this proof. It's only here for me. So the first theorem is, if you have an induced KRR minor, then you contain a generalized YT, or you contain one of those. So now I'm in a world where I can assume, I can make this board much stronger and exclude many more things. So I'm still going to exclude this. I'm going to exclude, let me switch colors again. I'm going to exclude this as an induced minor instead of an induced subgraph. And then here, this is not a cheat, this is easy. Excluding this and that as induced subgraphs is the same as excluding a binary tree as an induced minor. But I'm going to make it harder and easier on myself. I'm going to exclude some tree T as an induced minor. And so that's the world where I can afford to live now. I exclude those as induced minors. I have to exclude this as a subgraph. I exclude, I'm proving a stronger theorem for every tree. I try to exclude an induced minor. And now I'd like to prove that Pathwidth is bounded by Higginbotham's theorem. It's enough to prove the Treewidth. So now we've come to live in this world where no longer think so much about induced subgraphs. We can think about induced minors. And on the other hand, by this theorem, I can assume that there is by this theorem, I can assume that there is an R break as a subgraph. So there is an R brick. So now, this. I think to give it okay, which is why and before. Let me draw a small outbreak. Let me. So it's not really an outbreak, it's a bit of an outbreak. It's 3 vertices and many paths between every 2. So now this thing is very non-induced because if I could pick many of the, well, so first of all, if I could, if I had a pair of vertices with many pairwise anti-complete paths between them, if I could pick many of those, that would be very good for me, right? So suppose I have many of those. Well, in many, I can find a large complete subgraph of my KR where between every pair there are many pairwise induced, there are many pairwise anti-complete paths. So what I'm, okay, let me tell you what I'm really doing. So I color the edges of my KR by whether I can find many pairwise anti-complete paths between these 2 edges.
Pairwise
Anti-complete means no edges between them. So either there's a big click where I can or a big click where I can't. If there's a big click where I can, so if I can find a big sub click of my KR where there are a lot of pairwise anti-complete paths here, that's very good for me because if I can choose one from here, one from here, one from there with no edges between them, that's a subdivision of a big click. I contain anything I want. And if I can't, then many of these have edges to many of those. That's an induced KTT minor. So that's a good case. When I can find things with no edges between them, that's a good thing. So that means for many of these pairs, I kept their edges between all the paths. So now let's look at one pair like that. That's for historical reasons, it's called an unbreakable banana. So it's 2 vertices and many paths between them, but between every 2 paths there is an edge. So now, and let me not tell you how to do that. So it's interesting. Turns out you can walk a little bit on few of the paths and arrange it so that these red bits are anti-complete to each other. But each red bit has neighbors to a lot of the paths that remain. Each red bit has, so this is induced, it's really an induced claw, but from here I can get to a lot of paths. And from here I can get to a lot of paths. So now you contract this, you're in the world of induced minors, so you're allowed to contract connected sets with no edges between them. That's exactly what you're allowed to do in induced minors. You contract those and you notice that you found a slightly smaller brick in this contracted graph. So these are going to be the branch vertices. And then to go from here to there, I'll walk along this path until I get an edge to that path and back. So what I got is another in the contracted graph, but still free of everything I wanted because now everything I exclude is in induced minor world. And I found a smaller brick. And I found a pretty big brick. It's a smaller brick, but it's still a pretty big. So now look at a banana from this brick. And I can assume that inductively that here I can find whatever tree I want, just somehow I need to quantify that it's smaller. And the way it's going to be smaller, it will be lower height, but arbitrarily famous, right? So tree that branches a lot, but its height is smaller than the tree I'm looking for. So now you do it for many of these new bananas that you found. So there's some tree rooted at this and otherwise contained here, and there's some tree rooted at this and otherwise contained there. And now you look at all these very fat trees, and they're induced, they're really induced minors, these trees. So now you say, can it be that all the branches of this have neighbors in all the branches of that? Well, no, because that's a big KTT. So now you start with very fat trees, now you slim them down a bit. Now that they are very good to each other. So now what I have is, so now it's in the world of minors, but luckily that's where I want to be. It's a bunch of trees, trees T prime, which are height 1 smaller than the tree T I was looking for. And each of them as a root has this tractable path. And now you take that guy and you say, now I can join them all together and get the tree T that I was looking for. And that's how that's correct. That's it.
Questions? I wanted to ask, other than Pathwidth and Treewidth, do people study other target graphs that you want to, like grid width or?
So it makes sense to just ask, like, take any G, take any H, and ask, can you H decompose, like, can you get an H decomposition of G? And for example, if you can do it so that every bag has bounded radius in G. So what I
Radius is like a width?
it's like how far people are. So
Okay,
how
radius,
people, how far people are in G. Then they're quasi-isometric, the distances are more or less the same. So that's one example. It's it's not yet very popular, but I think it should be. I think it's a great topic. I try to inflict it on people all the time.
I have a question, but about a different topic.
Okay, so that's good.
I'm just curious.
Mhm.
So there are many theorems in this structural graph theory where some forbidden structure or other conditions imply that you can compute chromatic number efficiently.
Mhm.
Suppose I tell you that the graph is 3 colorful. Do you think that it's possible to color it efficiently with logarithmically manipulated?
So I think the best known is.
There's a polynomial bound. Yeah, there's a polynomial bound, but what information can you gain from the fact that the graph is 3 colorful? That is useful.
Right, yeah, no, that's a good question. I mean, I think people think that the polynomial is the truth, no?
I don't think anybody has really strong into it, but.
Okay. I don't know.
Okay, that's good.
I only know from what people told me.
Yeah.
Okay, thank you very much.